Should I share it already, Priya?
Yeah, I'll introduce you now, and yeah, you could share it.
I'll share it, yeah.
Yeah, just a minute. I'll introduce you, and then could you just hide that the hide thing? Okay. Yeah. Good afternoon, everybody. Thanks for being here on a holiday. It's a pleasure to have Shobna Narasimhan from JNC here talking to us about designing novel nanomaterials one atom at a time. Shobna has had a very illustrious career. She was a silver medalist in her master's from IIT Bombay. After that, she did her PhD from Harvard with David Vanderbilt. And then after two postdocs, one at the Fritz Haber Institute at Berlin and the Brookhaven National Laboratory in USA, she joined JNC in 1996, where she's currently a professor. Her research interests are well around nanosciences, examining various aspects. And she has several awards to her credit, which also include Fellow of the National Academies, the NACI and the Indian Academy of Science, in addition to the Fellow of the American Academy of Arts and Sciences, to which she was nominated last year. And she's actively involved in women in science activities in various capacities. And today she'll be telling us more about her work on novel nanomaterials. Shobna.
Thank you so much, Priya. You can hear me, right?
Yeah.
Yeah, okay. So as Priya says, it's a real pleasure to give this talk, and I thank you for inviting me to give this colloquium. I'll be talking about designing novel nanomaterials, one atom at a time. So this picture on my cover slide shows copper clusters with different numbers of atoms in them. The green atoms are copper, the purple are oxygen. So in this case, we were interested in when these clusters get oxidized or deoxidized, at what temperature oxygen gets removed from them. And this turns out to be strongly size dependent. So the number of atoms in the cluster matters. So if the cluster is small, this happens at a very high temperature. If the cluster is large, it happens at a low temperature. So this is an example of the kind of problems we look at. So I was told to make it a very general talk, so I have done that. So at least half my talk will be sort of introductory materials. So if you're a specialist in this field, which I know many of you are, I apologize for that. So what we do in our group is we aim to design new nanomaterials in silico, that is on the computer, using first principles techniques of density functional theory and a process of rational design. And I will explain all the words in this slide. So let me first start by talking a bit about materials. Of course, at SN Bose, you have a very strong material science initiative. So a lot of this will be familiar to you. So materials are so important that we define human history and progress by the new materials that started being used at that time. So we have the Stone Age, the Copper Age, the Bronze Age, the Iron Age, etc. Remember this Bronze Age because I will come back to that later. And this was sort of a joke about the Iron Age, and my students made me put this laughing cartoon here because they thought people will miss the cartoon about the Iron Age otherwise. So how many materials exist in nature? We have 98 naturally occurring elements and about 4,000 naturally occurring minerals. And these do have, of course, a large variety in their properties and therefore in what they can be applied to do, but we would like to do even better than that. So we aim to design new nanomaterials, that is those that do not exist in nature. So for someone like me, the periodic table is like my toy box, and the elements of the periodic table, the atoms, are the building blocks that we play with in order to design new nanomaterials. And we do this in silico, that is on the computer. Why do we do this on the computer? Well, nowadays, computers are becoming cheaper and cheaper, so it's much cheaper to do a computation than to do the experiment. I can work from home because this is something I really got to appreciate in the last year when many of us were forced to work from home. And I was fortunate that as a computational scientist, my work was not that much impacted when I had to work from home. This is important. It's often a lot quicker to do the computation, especially nowadays. It can lead to greater understanding. You can easily simulate conditions that can be very difficult to achieve in a lab. For example, if you want to go to very high pressures. So for example, if you want to see what is happening to, say, the iron that is at the center of the Earth, or to the gases that are at the center of Jupiter, or something like that. These are extremely high pressures. It's very hard to achieve these pressures in a lab, but in a calculation, it's relatively easy to achieve such conditions. We can switch off effects in a calculation, for example, relativistic effects or magnetism, and then see what happens. I will show you examples of this in my talk. And most importantly, we can make predictions for experimentalists to verify. And I said that to do this, we use first principles techniques of density functional theory. So I'll give you a 2-minute introduction to what is density functional theory. So here that introduction comes. So when we're dealing with the kinds of materials that I look at, the basic problem that you want to solve as a theorist is the quantum many-body problem, where you have a system with some number of nuclei and some number of electrons, which interact via the Coulomb interaction. So these can be atoms, molecules, condensed matter systems, and we can write down the equation for these particles. It may be the many-electron Schrodinger equation, or it could also be the Dirac equation. But because, and of course, the solution should be properly antisymmetrized. It has to satisfy the Pauli exclusion principle. But this is a very, very difficult problem to solve because of its many-body nature. So if we look at the different terms in the Hamiltonian, you have the kinetic energy of the nuclei, the kinetic energy of the electrons. You have the interactions between the nuclei, the interactions between the nuclei and the electrons, and the interactions between the electrons. Now, most of the time we make the Born-Oppenheimer approximation. So we can separate out an electronic Hamiltonian, which has these 3 terms. And then the problematic term is this electron-electron interaction, which is a many-body term that makes this a hard problem to solve. And density functional theory is one way of dealing with these troublesome electron-electron interactions. So how does one deal with a many-particle Schrodinger equation? If you are a condensed matter theorist or a material scientist, there are sort of 2 broad ways you can go about it. You might use the techniques of many-body theory, or like me and Priya and Tanushri, etc., you use density functional theory. In many-body theory, you retain the many-body nature and you use a model Hamiltonian. That is, you replace the Hamiltonian I just showed you by some model Hamiltonian like the Ising model, the Hubbard model, or something like that. And then you use a suitable parametrization, and then depending on your Hamiltonian, you may be able to solve it analytically or numerically. In density functional theory, on the other hand, You map this problem onto a one-particle Schrodinger-like equation. In principle, this mapping is exact, but in practice, this mapping is approximate. And there are no free parameters, unlike in many body theory, and it has to be solved numerically. So let me tell you a little bit more about it. So I told you that in density functional theory, you use something called the Kohn-Sham equations, where you map the many electron problem onto an equivalent one electron problem. So let me show you a somewhat frivolous analogy to what we do. So it's as if you have a system with a number of men and women with complicated interactions between them. If you like, you can think of the men as the nuclei and the women as the electrons. And they have complex interactions amongst them. And the problem you have to solve is that you have to arrange them all so that you achieve the optimal global level of happiness. And this is obviously a hard problem to solve because precisely of the fact that it is a many-body system. Now, what you do in density functional theory is that you map this problem instead onto this problem, where you have just one woman and you have to move her so that you achieve the maximum level of happiness. And this is obviously a much easier problem to solve than this problem. But the remarkable thing about density functional theory is that the solution to this problem is exactly the same as the solution to this problem, at least in principle. Now, obviously, it can't be quite that simple. Now, there is something extra that comes. There's an additional interaction that is introduced in the process of mapping this. You no longer have just Coulomb interactions. So you have this new interaction called the exchange correlation interaction, which I have schematically represented by drawing these face masks on the men. And I will return to these face masks in a minute. Okay? So in Dft calculations, you also call them first principles calculations or ab initio calculations. And why you do that is that the only input into the calculations, the only empirical input is atomic numbers and atomic masses. There is no other empirical input usually. So you input this, and then you crank through the machinery of your DFT code, and then you get the output that you want. So you input typically a structure and a composition, but you can also do calculations where the structure is your output, and then you do your DFT computations. Now, depending on your system, the calculation may be very fast. It may just take a second or two, or it may be slow. It might take some months to do. And the output you get is mostly very accurate results for the total energy of the system and various other properties of the system. So what kind of properties can you get? So I already mentioned that you can get the total energy of the system. So you can use this to calculate, for example, the geometric structure. Since you know in the ground state structure, the total energy will be a minimum. You can calculate the charge density. Okay, so these two I put smiley faces because the fundamental theorems on which DFT is based guarantee that the total energy in the ground state and the charge density are exactly the same for this fictitious one particle system for which you're solving the Kohn-Sham equations as they are for the many body system that you originally started with. The other thing you get out are electronic energy eigenvalues, in other words, the band structure. And here I put a sort of slightly doubtful quizzical phase because these are not guaranteed to be the correct eigenvalues, formally speaking. However, in practice, they often come out to be rather close to the true eigenvalues, and so we tend to use them rather a lot, even though this isn't formally justified. Now, all of this may sound too good to be true, and in some sense, it is too good to be true, because I told you that we have these face masks, and these face masks represent this extra term that is introduced into the Hamiltonian when you do this mapping, which is called the exchange correlation potential. And the problem about the exchange correlation potential is that we know there is an exact form of the exchange correlation potential which exists that makes this mapping from the many body system to the one body system exact, but we don't know what that exact form is. It's an existence proof, but we don't know what it is. So we don't know the exact form of this face mask. So if we knew the exact exchange correlation potential, then the solution of the one electron Kohn-Sham equations would be the same as the solutions of the many electron Schrodinger equation. In a way that I will specify means in the sense that the ground state energy and the ground state charge density are the same, but we don't know it. So anyone who, of course, this is an area of active research. I'm not involved in it, but many people are involved in it. So if anybody could design this perfect mask, could find the exact form of the exchange correlation potential, then you're not going to win just, a lot of money. You're pretty much guaranteed to win a Nobel Prize. Okay. So density functional theory is an extremely successful enterprise, so much so that if you look at the Phys Rev journals, the 10 most cited papers, in fact, I think the 16 most cited papers in Phys Rev journals are all connected to one aspect or another of density functional theory. On this slide, I have listed the top 10, and you can see that, they have like 100,000 citations, 90,000 citations, etc. The two landmark papers which started the field are this paper by Kohn and Sham and this paper by Hohenberg and Kohn. And the reason they're not at the top of the list is that they are such famous papers that people don't bother to cite them anymore for the most part. Otherwise, they would definitely top the list. And DFT codes can run on many platforms. Of course, most of us run them on HPC machines, but you can even run them on mobile phones. So this is a picture. Nicola Marzari, a friend of mine in Switzerland, ran it on his Nokia mobile phone. This picture is at least 10 years old, as you can probably guess by the fact that this mobile phone looks a little bit clunky and unwieldy. And the person who founded DFT is Walter Kohn. He has a very inspiring personal story because he grew up in Vienna and then he had to flee Vienna as a young boy. He was transported on what they call Kindertransport, which were these trains that took young Jewish children from Europe to England to escape the Nazis. And he and his sister were sort of smuggled out of Europe on these kinder transport, and the rest of his family died in the Holocaust. And then he went to England, and then when the Second World War broke out, he was imprisoned as an enemy alien because he was of Austrian origin. And it is in these prisoner of war sort of camps that he became interested in mathematics and physics. He was taught by other prisoners, and he became interested in physics and became a physicist. And for developing DFT, he was given the Nobel Prize in 1998. Okay, so I have told you about most of my aim. I still have to explain to you what I mean by a process of rational design. So I told you that there are about 4,000 minerals that exist in nature, but how many can we potentially make out of all the elements in the periodic table? There are these books called Landau-Bernstein, which contain lists of all the alloys that people have made. And, they fill shelf after shelf of a library in the days when people still went to libraries and consulted hard copies. So if you consider 9,000 crystal structure prototypes and only stoichiometric compositions, then it is estimated that you can make 3 into 10 raised to 11 quaternary compounds, that is containing 4 elements, 10 raised to 13 quinary compounds, that is with 5 elements, and this is not including nanomaterials. This is just extended bulk systems. So I told you I will return to bronze. So the Bronze Age is one of the famous prehistoric ages, and I find it very fascinating because bronze does not exist in nature. It's an alloy of copper and tin, and it's harder than copper alone, and it does not rust, unlike iron. And so the development of bronze was rather important in human civilization. Bronze was used to make weapons. The famous dancing girl statuette from Mohenjo-daro is made of bronze, etc. But what I wonder is, how did they know all those thousands of years ago? How did they find out that if they mix copper and tin, they could make this alloy? So if you look at all the materials discoveries in the past, they were either accidental discoveries or people developed them by trial and error. These are these 2 cartoons, not about materials discoveries, but about discoveries of the wheel. This cartoon is sort of speculating about an accidental discovery of the wheel, and this is somebody finding the wheel by trial and error. So in the same spirit, previous materials were found in one of these 2 ways. A famous example is the Haber process for synthesizing ammonia from nitrogen from the air and hydrogen. And this is so important a process that it has been called the most important scientific discovery of the 20th century. I realize people may have many other candidates for that, but I think this is a very interesting suggestion. And to synthesize ammonia from nitrogen and hydrogen, you need a catalyst. And about 2,500 materials were tested before they decided that they would use iron. In fact, iron wasn't even the best catalyst. Osmium was the best catalyst, but at that time, the world production of osmium was so low. Osmium was very rare, very expensive, and then iron was considered the next best candidate. But we don't want to do that kind of thing where you just systematically try thousands and thousands of materials for any desired application, which is a trial and error or brute force method. you want to do instead rational materials design, which requires a to and fro between theory and experiment.
I think there's a question.
Yeah, what's the question?
Shubhadeep, is there a question? Or maybe it was a mistake.
Sorry, ma'am, it was a mistake.
Oh, yeah, sure. Sorry. Yeah.
So in rational materials design, what you do is you take maybe, 3 materials, material A, material B, material C. You do computations on them. Then you analyze your results. And then hopefully, this is the hard part, you obtain some insight into design principles. And then once you've obtained this insight, you then can leverage that insight to obtain a new material with desired properties. Finally, let me say why nano very briefly. Again, this is something that I'm sure most of this audience is very familiar with. So why all the fuss about nanomaterials? The advantages of going nano are, of course, first miniaturization, then that you need a less amount of possibly costly materials. For example, nanocatalysts, you often have very costly metals like rhodium, iridium, palladium, etc. And so if you have a nanocatalyst, you need much less of those materials. And you may have enhanced properties. For example, you may have a higher magnetic moment, or it may be more reactive. And in my title, I said one atom at a time. So why did I say that? Because at the nanoscale, adding or removing one atom can make a difference. So this is, for example, the catalytic activity of gold nanoparticles for CO oxidation. On this axis is the reactivity. Here is the number of atoms in the particle. And you notice that, for example, if you have 8 atoms in your gold nanoparticle, it's a pretty good catalyst. But if you have 7 atoms, it's a lousy catalyst. And if you have 9, also it's not so good. So every single atom makes a difference. And similarly, if you have a layered material, then the number of layers that you have can be used to tune the properties. For example, this is phosphorine, and you see that the band gap of the phosphorine changes with the number of layers that you have. So for the rest of my talk, I'm going to give you brief glimpses of 5 projects that we worked on in our group. So these are sort of spread over the past decade, and I'll show you how we use DFT to understand the properties of nanomaterials and design new nanomaterials. So I will show you examples of all these things: how we can make a new material, how we can tune the charge of a nanomaterial, how we can tune its morphology, how we can tune its reactivity, how we can tune its diffusion and stability, and then finally, how we can tune its rotational properties. So I come now to the first one: can we make a new material? So alloys are made by mixing together 2 or more metals, but not all metals can be mixed to make an alloy. For example, iron and gold are immiscible in the bulk. You can't really make an alloy out of iron and gold. But we predicted that if you take a single layer, just one atomic layer thin of iron and gold, they will form a stable surface alloy, as it's called, if they are co-deposited on a ruthenium substrate. Okay? And after we made this prediction, experiments were done in the group of our collaborators, Sylvie Rousset in Paris. And this is an STM image of this system. So each of these black circles is an iron atom, and it is surrounded by 6 bright circles. Each bright circle is a gold atom. And this here is our simulated STM image obtained using density functional theory of the same system. So you can again see one iron atom, dark, surrounded by 6 gold atoms. Okay, so not only could we predict that this would be formed, and it was formed, and iron and gold are mixed at the atomic level, but we could also understand why this formed. So I had told you that in a Dft calculation, we can switch off effects. So what we were able to show is that the formation of this surface alloy is stabilized by magnetism. In other words, if we turned off magnetism, this alloy does not form, but if you turn it on, it forms. So the reason it forms is that when you form this structure, every iron atom, which is surrounded by 6 gold atoms, acquires a very high magnetic moment, and the resulting exchange energy stabilizes the whole system, and that is why this alloy forms. Now let me come to the next example, which is whether we can tune the charge on a material. Okay, so this flat molecule is cobalt phthalocyanine, and it is deposited on graphene, which has been doped with nitrogen atoms. Now, if this molecule is sitting on either undoped graphene, it is a neutral molecule. If it sits on a single nitrogen dopant, it acquires a slight negative charge. But if it sits on a nitrogen pair, that is, if there are 2 nitrogen atoms underneath the cobalt phthalocyanine molecule, it acquires a full unit of negative charge, that is 1 full electron. And as a result, the oxidation state of the cobalt changes, and this makes it a better catalyst. And we can see that in DFT also. So here, in these kinds of plots, which are called charge transfer plots, red lobes show that electrons have been gained. Blue lobes show that electrons have been lost. Here it is over a single nitrogen dopant, and you see that a little bit of electrons are gained by the molecule. But if it's over a nitrogen pair, you see a lot more negative charge is gained. And this is what changes the oxidation state of the cobalt center and makes the system a better catalyst. So the next sort of somewhat related example I'm going to give you is about gold nanoparticles. So here we are talking about whether we can change the shape and reactivity of a material. So supported nanoparticles, for example, nanocatalysts that for example, you have nanoparticles of precious metals on an oxide support in catalytic converters in cars, and they tend to clump up. That is, they tend to have these 3-dimensional shapes. So the question we have is, instead of this 3-dimensional shape, can we flatten it and thus make it a better catalyst? So in other words, if I have a seesaw, which denotes the energetic stability, in the gas phase as well as in oxide supports, if I, for example, consider a nanoparticle with 20 gold atoms, it can have this tetrahedral shape, or it can have this flat planar shape. And on the gas phase and on oxide supports, it's this 3-dimensional tetrahedral shape, which is lower in energy. But this one, which is high in energy, there's reason to believe that it might be the better catalyst. So what we would like to do is to tilt this energy seesaw so that this one now becomes lower in energy than this one. And this is a problem that lots of people have looked at in the field of nanocatalysis. Here are some of the papers that people looked at this question in. And so this is sort of just a silly COVID joke. Our goal is to flatten the curve, or rather to flatten the nanoparticle. And another silly COVID joke is, how do you flatten the nanoparticle? So this is a joke that if you just wait while you're in lockdown, curves automatically get flattened. Okay. So what we thought of was that if you have this three-dimensional nanoparticle, which is supported on a oxide support, and you dope this support, that is, you take some of these gray divalent magnesium atoms and replace them with these purple trivalent aluminum atoms, then there are electrons floating around because of the aliovalent doping, and these electrons may get transferred to the nanoparticle and end up flattening it. So does this work? We did Dft calculations. So this shows the energy difference between the planar and tetrahedral shapes of the nanoparticle versus the concentration of the aluminum dopant. So at small dopant concentrations, the three-dimensional shape is still favored, but above about 0.4% doping, you find that the planar shape is indeed favored. And soon after we made this prediction, the experiment was done. The experiment was done on a slightly different system. Instead of a magnesium oxide support, they used a calcium oxide support. So here you see an STM image, gold nanoparticles on undoped calcium oxide, and they have these three-dimensional morphologies. And when you instead dope the support, in this case, instead of doping with aluminum, they doped with molybdenum, then you see you have this change in morphology. You have these flat shapes of the nanoparticles, okay? They are just one atomic layer thin. So this strategy that we predicted actually works. So I've shown you two examples so far where a prediction was made by DFT and it was confirmed by experiment. And of course, we went on to confirm also that this is true for this system. And incidentally, these nanoparticles are much larger than 20 atoms in size. So that shows that this strategy works for larger sizes also. And we've also done calculations on smaller sizes and shows that it works for smaller sizes too. So what happens, just like in the cobalt phthalocyanine case, once again, you have this red lobes showing charge being gained by the cluster. It has been lost by the support and it is transferred to this nanoparticle, which then flattens out. Now, this charged cluster, there is reason to believe that it will also be a better catalyst for certain reactions. So we can check that. So in DFT, we can also compute barriers for certain reactions. So for example, here the reaction that it's being computed for is the dissociation of this oxygen molecule, which is shown here in blue. You can see that the molecule is slowly, the two oxygen atoms are coming further and further apart, and finally the molecule is dissociating, and you can compute the energy barrier for this. And if we compute the dissociation barrier on the undoped support, where you have a three-dimensional nanoparticle, the dissociation barrier is 0.68 eV, whereas on the doped support, where you have the flat cluster, the barrier is significantly reduced to 0.29 eV. Now, if you assume that the prefactors are the same, etc., and you put an exponential term in, then this assumes that reaction rates, this would imply reaction rates were increased by about 5 orders of magnitude at room temperature. So it suggests that it indeed should be a better catalyst. Now I come to the next example, which is about diffusion and sintering of ultra-small supported metal clusters. So the question here that is, can we understand the diffusion and stability of a metal? So the kinds of clusters that I've been talking about, the kinds of nanoparticles that are supported on an oxide support, for catalysis, etc., you want small nanoparticles because they are believed to be more active. However, these small nanoparticles are not stable. It is always energetically favorable for them to diffuse and coalesce and form larger nanoparticles. This process is called sintering. So I'll show it to you here. This is an electron micrograph. You already saw these two nanoparticles coalesced and formed a larger nanoparticle. And if you watch this video for a little while longer, you will see that these two nanoparticles also will diffuse and coalesce. And so ultra small supported metal clusters, though they are good catalysts for many reactions, are unstable to sintering. So we would like to understand how this process of sintering occurs. Are all metals equally likely to sinter? And also, what is the process by which sintering occurs? This kind of process shown in this video is what's called particle migration coalescence. But you can also have processes where one atom at a time is added to a nanoparticle and it grows by such a process. So the first thing we studied is how nanoparticles move. And we found that the processes by which they diffuse, by which they move, is extremely sensitive to the element that the nanoparticle is made of, and also to the number of atoms that the nanoparticle is made of. So here I'm showing you the diffusion of a single platinum atom, that is this purple atom, on a magnesium atom support. Okay, and it is diffusing by this process. So this is not just an artistic animation. This is an actual DFT path obtained by using a process where we combine density functional theory with something called the nudged elastic band method. So the particle hops along the surface and we can calculate the energy profile for this. So it has a minimum where it sits above an oxygen atom, and then it sits at a bridge site, that is the transition state, and then again a minimum. And we can calculate the barrier for this hopping process, and it's 0.88 electron volts. However, if you look at a dimer of platinum, then it does not move by this simple diffusion process. Instead, it does this kind of cartwheeling process where the dimer lies flat, then sits vertically, then lies flat and sits vertically. And you see you have a rather more complicated energy profile for this process, and the barrier is much lower. It's 0.42 electron volts. If you have a trimer of platinum, it has a third diffusion mechanism. It is neither the cartwheeling nor the hopping. And I don't know how many of you have seen the Star Wars movies, but in the Star Wars movie, there are these transports called AT-AT walkers. And this sort of slow, ponderous diffusion of this trimer reminded me of the AT-AT walkers in Star Wars. And so I called it AT-AT walking. And this is the profile for that process. And this is the barrier of 0.6 electron volts. And if you look at the tetramer, that is 4 platinum atoms, you have yet another process, which is rolling. Okay, so we can calculate the barriers and the mechanisms for different sizes and different elements. And one thing that we found, which was quite surprising, this is an example for the trimers, but is that if you plot the diffusion barrier, the barrier for diffusion for trimers versus the melting temperature of the bulk metal. So this is silver trimer, gold trimer, palladium trimer, platinum trimer versus the melting temperature of bulk silver, bulk gold, bulk palladium, bulk platinum. You get this beautiful straight line. So the diffusion barriers scale, in this case, perfectly, for other sizes, at least approximately, with the bulk melting temperature. And this is pretty non-intuitive and surprising. You wouldn't expect that for such small, ultra-small clusters, something should scale with the property of the bulk metal. But we actually did an investigation of why this occurs. We were able to show that, the diffusion barrier scales with bulk binding, with the binding energy of the cluster, which in turn scales with the cohesive energy of the bulk metal, which in turn scales with the melting temperature of the bulk metal, etc. And we also showed that for this scaling relation to happen, you should have a parabolic diffusion path between the global minimum and the transition state. And this is true, like you have this roughly parabolic path for the tetramer, you have it a roughly parabolic path for the trimer, but you don't have it for the dimer. And indeed, if you check for the dimers, this scaling relation doesn't hold. So the scaling relation does not hold for the dimers, and we also understand why it doesn't hold for the dimers. And using this data, we can also look at the sintering mechanisms. We can see how the particles coalesce. So we see, for example, that for platinum, the way they coalesce is they coalesce by one atom being added in a stepwise function. So it goes from 1 to 2 to 3 to 4. But it's an unexpected way. I say unexpected because you would expect that it would be the single atom that would diffuse and get attached to the larger particle. But instead, in the case of platinum, it's the larger cluster that diffuses and gets attached to the single atom. Whereas in gold, there's a different mechanism operating. It's more what we call particle migration and coalescence, where particles migrate and coalesce. So for example, see the contrast between this and this. And so you have growth by particle migration and coalescence. Now I come to my last example, which is, can we understand the movement of molecular machines? So this is again an STM image. Let me get rid of my pointer and play this video. So the molecules colored gold and the molecules colored silver are actually the same species, but they're colored for visual clarity, they've been colored differently. And the ones colored silver act like guest molecules, and the ones colored gold act like host molecules, and the ones collected silver rotate. So if you watch, you can see them rotating, but it's a very punctuated rotation. They switch between different orientations. Okay, so these are these molecules called BPPCOOH on silver 111. So these are STM images done by an experimental group at TU Munich. And we can study this. So you see the video, and we can study this using density functional theory calculations. So this is an atomistic view of these molecules. And here, these yellow and green lobes are like the blue and red lobes I was showing you before. They represent electron accumulation and depletion, and each row of alternating yellow and green lobes represents a hydrogen bond. So now I will play this video, and you will see in our theoretical calculation, we can see the molecule rotating, and as it rotates, you can see that bonds are formed and broken, and accordingly, the energy changes according to this graph shown at the bottom here. So the red dot shows where on this energy landscape you are as you rotate, and you can understand why you have high energy at some places and low energy at some places. You have low energy where the structure is stabilized by the formation of lots of hydrogen bonds, and you have high energy where you have very few hydrogen bonds. And so we can study this whole energy landscape, and you can understand the dynamics of the rotation. And I haven't shown those results here, but you can deduce the barrier for the rotation from the experiments, and you can also compute the barrier from our Dft calculations, and they match exactly, almost correctly. It's about 0.94 electron volts. This structure also has some interesting chiral features, which I won't go to. So I am done. I've sort of just given you an overview of things that we worked on. And the take-home message that I want to leave you with is that density functional theory, when used in tandem with experiments, can be used very successfully to understand why materials possess the properties they do. And then one can use this understanding to design novel nanomaterials with desired properties. So acknowledgements, these are the people I worked with. The first group are current or former PhD students of mine. Stefano de Gironcoli is at CISA in Trieste. The next group of people are at the University of Paris Diderot. And the next group of people are at Technical University Munich. And for funding, we had it from the Indo-Italian Program of Cooperation, from CEFIPRA, the Indo-French Center, from Technical University of Munich, and our computational resources were from the Thematic Unit of Excellence of Computational Material Science, which was funded by the DST Nano Mission. And I am done. Thank you very much.
Yeah, thanks, Shobna, for the very nice talk. And yeah, my first question to you would be, where did you get all these animations from, especially the cartwheeling and... Yeah.
Well, do you mean the molecules or the people?
The people.
Oh, well, Google search, of course. Google image search is very good.
Even then, anyway. Okay. So talk is now open for questions. Could you just raise your hand and... Yeah, Rajdeep, yeah, go ahead. Oh, unmute and ask.
Yes, ma'am. I am very much happy to see the animated presentation for the first time.
Okay.
And my one question is that from animated presentation, when you are saying that cartwheel type of movement, like for dimer, monomer, and tetramer,
Yeah.
you are showing the energy profile. But I am unable to understand, if I try to solve the equation of motion, can I get the same number of minima? Like for dimer, tetramer, the number of, and even for monomer, the number of minimas and maximas are different. And there are many.
So it's actually so what I have done. So it's a complicated. The energy landscape is very complicated. There will be a global minimum. There'll be lots of local minima, lots of local maxima. So what we do is we find first the global minimum, which is a hard thing to do. And then once we find the global minimum, we search for the lowest energy path between one global minimum and the next global minimum. And to do that, there's a technique called the nudged elastic band. So we use this nudged elastic band to find the path, the lowest energy path between one global minimum and the next global minimum. Okay, and this path that I have shown you is the path that is found by that nudged elastic band algorithm. And indeed, you will find that it is different in the case of the monomer, dimer, trimer, tetramer, etc.
Okay, ma'am, it is not like the simple Lagrangian or Hamiltonian approach of MSc days.
No.
Okay, okay, ma'am. Thank you.
I mean, you can also do that. You can also do what you're saying, which you would do using something called molecular dynamics. Okay, if you did what you did, you took the equation of motion. You can do that, and you can solve with molecular dynamics. The reason that you don't do that is that these jumps from one position to another are actually rare events. Like you will have to wait a long time. It will spend a lot of time sitting at one global minimum before it jumps to the next global minimum. Like what I showed you, it just kept walking, 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 walking. Now that's actually a little deceptive. It will actually sit a long time in one global minimum, then take one step to the next global minimum, then stay there a long time, and then take the next step. And it will be a kind of random walk between these global minima. And if you want to do that with molecular dynamics, you need a very, very, very long simulation time. So that is why you do it with this alternative approach, which is called a notched elastic band approach.
Thank you, ma'am.
Yeah. Are there any other questions? Otherwise, I have one. So you had this copper thiophene or whatever it is, COPC, sorry, cobalt COPC on graphene.
Yeah.
And so essentially what you did, there were two things. One thing was your nitrogen doping the substrate.
Yeah.
Okay. And then you said that you actually changed the charge state of cobalt. So what was the percentage of nitrogen doping?
So, so the percentage is, well, so in our calculations, we actually, in our unit cell, we actually put just one nitrogen or two nitrogens, etc.
Okay.
And in the experiments, they had like, whatever, 0.5%, 2%, something like that. But the thing is, it is not uniformly
doped.
Uniformly. Okay. So in some cases, you have two dopants very close together. Some cases, you have only one, etc. And that they can see with their STM. So where they have two, where it sits over two, they can, with their scanning tunneling spectroscopy, they can actually measure where the LUMO is, where the HOMO is, etc., and therefore deduce the charge state. Okay. And from that, they're able to see that there's a big difference in the charge state when it sits over 2. Now the question is whether you can then engineer a device so that you actually have dimers. Because here it happens by accident. They haven't engineered it so that there'll be dimers. When they dope it, they get some monomers, some dimers, etc.
Okay. Yeah, and related to that is, so you changed the charge state, and you said it also changed the catalytic activity of the molecule.
Yeah.
So was it some particular, what do you call it, orbital, which then became unoccupied, and that's the, so what's the way one should think of the increased catalytic activity?
Yeah, I suppose so. I guess it's the d orbital. It's probably the d band center moving. We didn't actually calculate the catalytic activity in this case, which is why I didn't talk about it. It is known experimentally that change the charge state, but I guess it must be the d orbitals of cobalt where the d band center probably shifts.
Okay, and Tanushree has a question. Tanushree, you can go ahead and unmute yourself and ask it. Is she there? She has some network.
Yeah. Can you hear me now?
Yes.
Yes. So I think you had in one example of formation of a surface alloy where you mentioned that the magnetism is being responsible for such kind of immiscibility because in bulk it's immiscible.
Yeah.
But then in bulk also you have the magnetism. Is the nature of magnetism different when you go to the surface?
Yes, it's because you have lower coordination in the surface. So the magnetic moments, the enhancement in the magnetic moment is, the iron has a much less coordination. And so the hybridization of the iron is less when you have a single atomic layer. And so you are able to achieve a much higher magnetic moment in the surface alloy than you can have in the bulk alloys. And that is why it forms a surface alloy and not a bulk alloy.
Yeah. So how much is the kind of enhancement if you have it top of your head? Or I'm just curious.
I think it almost became 5 Bohr magneton, if I remember correctly.
Okay. Thank you.
Yeah. If there are no other questions, we thank Shobna for a very nice talk. And yeah, we'll close the session now.
Okay, thank you very much. Bye.
Thank you. Bye.
Thank you, Shabana.
Bye.